Hey guys, I have your notes here for section 10.3, day 1. And before we begin, you might want to grab your homework where you wrote out several terms of your Taylor polynomials to approximate a few common functions. So this is going to help us today. We're going to start getting into, now remember, a Taylor polynomial is just several terms written out, but we can't really write them out forever. We have to stop them somewhere. When we stop them, that's called a Taylor polynomial. When we give a representation of all of them, we usually use the summation symbol, and a series is the word that we use to represent all of them. We can't write them all out, but we can write them in series notation and summation notation to represent a series, and that gives the representation of all of them. Whew, that was hard to say. So, what we're going to do, we're going to talk about how closely does a polynomial match a function. Can we make it match better if we take the polynomial out farther? We're going to look at error. We're going to look at how far off is it? If I stop it here, how far off is it? Things like that. We're going to look at things like that this section. So, in your sheet that has all these on it, keep in mind, in order to generate a new polynomial for a new different function, you can always start with these and manipulate them. For example, your e to the x polynomial is here. Well, you could make a polynomial, a Taylor polynomial, to represent e to the x squared. You just sub in x squared everywhere there's an x. So you can manipulate by substitution. You can manipulate by doing derivatives. So let's say that you want a polynomial for the derivative of this top one, which is the derivative of 1 over 1 minus x squared is going to be negative 1 over quantity 1 minus x squared times negative 1 because it's so it's going to be 1 over the quantity 1 minus x squared. You can find your polynomial for that quickly by just doing a derivative on all of your terms. Okay, so just a reminder, you can manipulate your polynomials and find new ones quickly. So let's do that. In your notes, the first one it asks for is a new polynomial for not cosine of x, but cosine of pi over 2x. So all I did was I wrote out my original cosine Taylor polynomial, and I just subbed in my new angle everywhere. Now, the directions asked for, I forget, the first 4 non-zero terms. Okay, I can do that. And the general term. The general term is what's tricky. That's what would go in your summation notation. That's tricky. So, I'm going to start simplifying, and this middle row here is going to help us with our general term. So I started to simplify. So really all I did was I squared everything and then realized my 2 squared can move down to the denominator, right? Raised everything to the 4th, move that down. Raise this to the 6th, move that down. Yes, I'm going to keep going to simplify it for the answer to the question when it asks for the first 4 non-zero terms. So this is half of my answer. The first 4 non-zero terms simplified. So I have multiplied everything out. However, when I go to make my general term, I'm going to back up here to when everything still had an exponent on it. Before I cancel anything, before I square or multiply anything, this is going to help. This is going to be the one to help me see my general term. And what I would do is I would come down here and somewhere kind of tiny, I would say, okay, that's my term when n is 0, n is 1, n is 2, and n is 3. And it's fairly easy to see how you're going to come up with these things. So when n is 1, I think I want pi to the 2n. pi to the 2n, pi to the 2n. I like it. When n is 1, oh, and also it works back here. When I do pi to the 2 times 0, no pi left. X to the 2n, x to the 2n, x to the 2n, x to the 2n. I like it. And then 2 to the 2n, I like it. And then what is being factorialed is 2n. And it alternates. Whew, holy moly. So the general term, I'll do the alternating part first. I need -1 to the n. Yes, is that right? I don't want like n plus 1 or n minus 1. I need -1 to the 0. -1 to the 1. -1 to the 2. Yes, I like it. I need pi to the 2n. I need x to the 2n. Yes, you could have written those together in a parentheses to the 2n. I need 2 to the 2n. And I need 2n factorial. There we go. That's my general term. And yes, in fact, all three of these, you could have put these in their own little fraction and said that the whole fraction is to the 2n power. That would work too. It's kind of hard grading your tests sometimes because everybody sees it differently and writes it differently. And sometimes I have to sit there literally on your test and write out what you did to make sure that the way you wrote it matches the way I wrote it, even though we saw that completely differently. Okay, next one. So we're going to make a new polynomial for cosine of x, quantity squared. Now, I don't even think I need to waste my time saying this, but you know that if you square cosine x, you cannot square each term of a polynomial, right? Because even on a binomial, you know you have to FOIL it out. If you square a trinomial, oh my gosh, you're going to end up with 9 terms, and so on and so on. So, yeah, I can't do that. So what you're going to do, you're going to use the hint of the trig substitution that I think we used it in the last chapter. Maybe, yeah, I think we did. 1/2 times this quantity. So what we're going to do is we're going to start with cosine of 2x and just kind of build it up from there. We'll make a polynomial for cosine of 2x. We'll add 1 to our polynomial, and then we'll take our entire polynomial and multiply it by 1/2. So I've already done that. Cosine 2x, obviously just subbed it in. Next step, I added 1 to both sides of my equation, and I simplified these just a bit, but not too much, because I still want to come up with that general term. Right? I mean, add 1, there you go. Simplified these just a bit. And then took both sides and multiplied by 1/2. All right, now when I multiply both sides by 1/2, this cut in half, obviously. This term, when I multiply by 1/2, I lose one of my powers on my 2. This term, when I multiply it by 1/2, I lose one of my powers on my 4. Or on my 2. Here, I lose one of my powers on my 2. So this becomes my new unsimplified first 4 non-zero terms. This is what you and I will together look at to come up with our general term. I went ahead and I did simplify it up here. And in fact, when I was working this out before starting the video, I went too far. I was like, oh my gosh, how am I going to back up? So this is part of my answer that the problem wants. There are the first 4 non-zero terms. So for this one, again, I think I'm going to go just a little note to self. N is 0, N is 1, N is 2, N is 3. This just helps me be able to see it. All right, so first of all, we need it to alternate. So we're going to need a -1 to the 2n power. Couple things. 2 to the first. Oh, is it 2 to the n? 2 to the n. No, it's not 2 to the n. And also notice your exponents on your 2 increase by an increment of 2. So my exponents, 1, 3, 5, it's a linear relationship that my exponents have. The 1 and then the 3 and then the 5 and then it's like a line with a slope of 2. You just have to figure out where it starts. So I think this is going to be 2 to the 2n plus or minus something. So if I do 2 times this, I need to shrink it back by 1. 2 times this, shrink it back by 1. 2 times this, shrink it back by 1. So let me write this down before we forget it. We need our alternating portion. I need 2 to the 2n minus 1 power. What else do we need? Got that? I need x's. So x's increase by 2, 2n. Do I like it? 2n, 2n, 2n. I like it. X to the 2n. Over 2n factorial. Oh, hold on. Quantity factorial. There we go. There's your general term. Okay, fun stuff. Next one. Let's see. Next one, we're going to need our graphing calculators for this one. Find a Taylor polynomial. Okay. Let's get our error within here. So let's take our Taylor polynomial out far enough to where the difference between the function and the polynomial is within 0.0001, right? Because at zero, our polynomial matches our function perfectly. Okay? But then the farther out we go from 0, you've seen pictures, those two functions are going to start to separate a little bit. So we're only going out to like negative 3.14 and positive 3.14. That's as far out as we'll go. But when I go out that far, I want them so close to each other that the error is less than, the difference between the two is less than 0.0001. Okay? All right, so I've written out a few of my terms of my Taylor polynomial for sine x, and I'm wondering, is a 7th order polynomial good enough? Have I gone out far enough to where the pink function mimics sine? Hang on. Mimics my sine curve within 0.0001. Alrighty, so here's what we're going to do on our calculators to see. And I'm going to call the difference between the two the error, because once this starts heading away from this, it's not, I get some difference. I get some wrongness in there. This is no longer perfectly matching this, so I'm going to call it the error. So what we're going to do is we're going to look at error. And I really don't care if the error is positive or negative, so I'm going to put absolute values here. Let's take our original. Let's subtract our approximation. Right? I don't care which one's on top, which one's on the bottom. So I'm putting the absolute values on there. Just how much off is this one from this one? How much off is this one from this one? We're going to call it the error. Okay, so we're going to type this in our graphing calculators. So I am going to switch over. You're going to lose my notes here for a minute. I'm going to switch over to my graphing calculator. Okay. There we go. Now, here's what I did. You're going to need to pause the video if you're doing this with me, because this is going to take you a while. Mine's an older model graphing calculator on, because this is a very older model of a computer that I'm hooking up to. But when I hit absolute value, I don't get the bars like most of yours will. I just get ABS for absolute value. It's fine. It's all good. Still works. Still works well. So I've got absolute value, and do you know how to get to absolute value? You hit math. Let me go down here so I don't mess it up. If you want an absolute value, you go math, and then over 1, right there, and hit enter. All right, so absolute value. And then I did sine x, that's my original, minus parentheses. Now start typing it all in. I've got x minus x to the 3rd over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial. You need to know where the factorial is? I got you. Math, over, 4th option. All right, so when we type those in, also, I set my window. So remember I said we're only going out in each direction from 0 to, we're going to go out to negative pi and positive pi. So I set my x min at negative pi and my x max at positive pi. I don't care what we're counting by. Y min. What is y? Well, y, we just typed it in. Y is going to be positive because I absolute valued it. It's the difference. It's the difference between the real function and my polynomial representation. It's the difference. I want that difference to be within 0.0001. So I set my y max to be 0.0001. Now I graph it. Okay, here's what you're looking at. I need to write on this. Let me pull this up for a second. Sorry about the glare. Ignore that part. Cover your eyes. Just kidding. So what do we got here? This is negative pi. This is positive pi. This highest y value up here is 0.0001. It's little. That's hard to see, isn't it? So what are these two corner points right here? These two corner points, I know that my graph doesn't touch them, but here's what the corners represent. This corner represents this x amount and this y amount. And likewise over here, negative pi and that y amount, okay? This blue thing is my function. What do you think? At pi, is my y value on the blue function? At pi, is my y value on the blue function higher than 0.0001 or lower than 0.0? If you could extend it out to here, where is the blue function? The blue function is way up there. I need, this is what I need. I need my y value. What y value? It's the difference between the function and its representation. It's the error. I need the error to be within, I need my y value to be within 0.0001. We need to add more terms to our polynomial. So, you're going to go back to your y equals and type in one or two more terms and see what that gets you. Now, to do that, I'm going to put my cursor on my parentheses and I'm going to press insert. I don't want to retype everything. I just want to insert a few more terms behind my subtraction there. So I'm going to go second, insert. Now see how my cursor changed? Now, my next term is going to be positive, so I'm going to put a plus. My next term is going to be x to the 9th over 9 factorial. Let's do one more. X to the 11th probably faster than me because I'm on this ancient computer. Almost. Almost. So, there, this one finally caught up. If I go over as far as pi, this is still going to be way up there. You can try, let's try one more. And my 13 is going to be positive plus. That did it. Adding that one more term. That one's not going to catch up. That's okay. Adding that one more term took my y value to something lower than 0.0001. So when I go out the distance of pi, my y value is less than that. So how many terms did it take me? Well, it took me at my 13th order because I had to go through the 13th derivative. Okay, so I'm going to unhook there, go back to our notes, and let's write our answer. Find a Taylor polynomial. Okay, so turns out my answer is minus plus x to the 9th, x to the 11th, final answer. And you can even call that P13 because we went out to the, basically we went out to the 13th derivative. Alrighty, last one. This one will go quickly. Find a formula for the truncation error. Now remember, error is what we get when we cut off the polynomial, when we cut off the, when we cut off the series. When we cut off the series, we get a polynomial. How far off is the polynomial from the function we're trying to represent? So we're going to truncate right after x to the sixth. We're going to truncate there. So all of this, these are my leftovers. So my truncation error for this geometric series is, just kidding, is that one plus that one plus that one, and on and on and on and on. It's a geometric series. How do I represent this new series that I just made? It's the sum. I'm adding everything. It's a series. How do I represent all of this? Well, this is my first term of my everything that was cut off. This is my first term, and I'm multiplying by x squared every time. How do I write the sum of all of that? I write it as sum equals first term over 1 minus r, which is x squared. Find a formula. That's my formula. And again, how did I get all that? Well, I cut the series off here, turn this into a polynomial. If we're just looking at a polynomial, we know that when I do this math, I'm not quite going to get this. Why am I not quite going to get it? Because I left out all of this. If I leave out all of this, then this won't equal that. How much will it be off? It's going to be off the amount that I cut off. So this is basically my error. The amount that I am ignoring is my error. It's called a truncation error. We wrote that as its own little series, and then we used just basic summation notation or summation formula to come up with that. Alrighty. That's going to get you through. Good luck. Hope you're going to get off to a good start on section 10.3.